Assalamu alaikum, everyone. Welcome back. In the last class, we were talking about solar tower power plants, and we basically started watching this very interesting video on 100 megawatt solar tower plant in China. I encourage all of you to go back and watch this video. It discusses a lot of practical implications of setting up a solar tower plant, how how frequently you need to clean the mirrors, how big the mirrors are, and what options are available. How do you select a location for setting up a solar tower plant, and a lot of very interesting stuff. So it's just a 8-minute video. So I strongly encourage you to go and check it out. Now, what I want to do in today's class is basically to complete the discussion on solar tower plants and solve a problem, right? So let's assume we want to set up a solar tower plant in Tehran, and uh, it we have decided to have heliostats which have a total area of 80,000 meters square, right? So a lot of heliostats over a very, very large area. And these are being used to reflect the radiation onto the receiver. Now, the solar radiation is 950 watt per meter square, and the steam is being produced at 2 megapascal and 400 degrees Celsius because of uh, energy exchange from the uh, molten salts that are heated by the solar tower, right? Solar tower receiver. And so we generate some steam from it, and these are the conditions for the steam. And this is the rate at which the steam is being generated. Now, of course, once you generate steam, then you expand that in a turbine, and we expand it in a turbine to 20 kilopascal. Uh, so the isentropic efficiency of the turbine is given as 85%, and we can neglect the work input to the pump, right? Simply because it's usually negligible for a Rankine cycle. Now, for the above information that is given, we simply need to calculate the work output of the turbine and the thermal efficiency of the solar tower plant. We have a lot of information provided to us, all the relevant ones, and here we know the inlet to the turbine, 2 MPa and 400 degrees Celsius. We know that if it was an isentropic process, which it is not, uh, process the at the end of the expansion, the steam or the saturated mixture of liquid, water, and vapor would be ending up at state 2s, but it's not isentropic. So in reality, there's going to be some increase in entropy, and it shows up at state 2, right? Now, in terms of calculating the work output and thermal efficiency, it's very simple. The first part is actually very simple. It's just the usual thing that we do. So work output of the turbine. And since we are neglecting the work input of the pump, so when we talk about the net work output of the turbine, it's simply the what happens in terms of, in the turbine itself, right? So mass flow rate of the steam times enthalpy in minus enthalpy out from the within the turbine. Enthalpy at the inlet, H1 can be determined based on the information given, 2 megapascal and 400 degrees Celsius. For determining H2, it's a slightly long process because we have to do it in a two-step way. So first thing is we need to determine the enthalpy of the isentropic state H2S. And can be simply determined because we know the pressure at state 2. Okay, pressure at state 2S is going to be pressure at state 2, which is 20 kilopascal. All right. So for state 2S, which is the isentropic state, we also know that the entropy is going to be equal to S1. So we have the entropy from state 1, we have the pressure. Using this, we can fix the state 2S and get the enthalpy. Now, once you have S2S, then simply you can make use of the isentropic efficiency formula for a turbine, which is the actual work output, H1 minus H2, divided by the isentropic work output, H1 minus H2S. We have everything here, H1, H2S, and isentropic efficiency given. So from here, we can find H2, okay? And essentially, that's what we'll be doing it here, right? So basically, this is our formula. We have H1 and S1 based on these properties. And we have the pressure for state 2S. The entropy is same. We can calculate H2S. And then from the definition of isentropic efficiency, we can calculate H2. Okay, so once we have S2, we have everything that we need for calculating the work output, and you plug in the numbers, and we can get the work output. Now, when we talk about the thermal efficiency of a plant, for a solar power plant, we define it as the network output divided by the uh, the 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 solar radiation incident on the plant itself, which is the solar irradiation G times the area. Now here the area is basically the area of the heliostats, because they are the ones that are receiving all the solar radiation, which is coming at a rate of 950 watt per meter square. So we simply have to do it as 15,280 kilowatt, which is of course, the work output from this turbine divided by the solar irradiation G in kilowatt. So we have 0.95 kilowatt per meter square multiplied by the area of the heliostats, 80,000. Okay. Once you do this, it comes to about 20% efficiency. All right. So you can see that the efficiency of this plant is kind of similar to what you can see from a solar PV. In fact, it's higher than solar PV. Okay. But all of these calculations that we did, they apply for a certain time of the day or certain day of the month where you have irradiation of 950 watt per meter square. It is not that you have this amount of radiation every day or any time of the day, right? It varies from day to day. It varies from morning to afternoon to night, right? Of course, there's nothing at night. Now, let's move on and solve the other part of the problem. So here the question is how much electricity can be produced per year, okay, annually, if the average thermal efficiency is 15% and generator efficiency is 96%. So now what we are saying is, okay, on an annual basis, the thermal efficiency comes out to be 15%, which is exactly the same as what you get with solar PV, right? Uh, or very close to what you get with solar PV. And for this overall annual efficiency of 15%, we want to calculate how much electricity can you produce on an annual basis. So if you want to find out how much electricity we can produce on an annual basis, we need to understand how much solar radiation is being incident on an annual basis. Now, since we are looking at building this solar tower plant in Tehran, it makes sense to look at the radiation for Tehran. Okay, and as we discussed before, there are multiple definitions for radiation. You can look at beam radiation or direct normal irradiance (DNI). You could look at diffuse horizontal irradiance DHI, or you could look at global horizontal irradiance DHI. All of these are different definitions, and they will be useful for different kind of solar energy conversion devices. When we talk about concentrated solar devices, which make use of beam radiation, we have to see DNI, because it's the beam radiation or the direct radiation that comes from the sun that is used for that is being converted to more useful forms of energy, right? Radiation, solar radiation being used to convert it to more useful form of energy. So for all concentrated solar systems, we have to make use of DNI to scale our system to calculate its energy output and so on and so forth. So for the DNI for Tehran on an annual basis is 1843.6 kilowatt hour per meter square. Okay, I got this information from Solar Atlas website. You can get this. You can get the average annual or a daily average DNI or GHI or any other radiation information from Solar Atlas for any location. So it's a very useful website. Now, once you have that, we can simply calculate the product of effectively G times A, right? We want to calculate how much solar radiation is actually hitting those surfaces, the heliostat surfaces. Okay, on an annual basis, it's just going to be the radiation times the area. Okay, and this radiation times area gives us the total amount of energy, the solar radiation that's hitting the heliostats. Out of this total amount that's actually reaching the solar tower plant, 15% is being converted to electricity. So 15% of this total amount gets converted, sorry, it gets converted to the work output, right? Not to electricity, sorry, because we're talking about thermal efficiency of the turbine. Yeah. Um, so yep, work output of the turbine is simply thermal efficiency times the energy that is coming and hitting the solar tower plant, right? Reaching the solar tower plant effectively. So when you do the math, 15% times the total solar radiation uh, that's reaching the heliostat surfaces, so we can get 22.12 into 10 power 6 kilowatt hours. Okay. Now, this is the total amount of work output from the turbine on an annual basis per year. Okay. It's not per day, but per year. So we want to calculate how much electricity can be produced, right? So if you want to calculate electricity, well, work output does not give us electricity. You have to use a generator, as we already know. So you have to take in the generator efficiency into account, right? So this quantity, the work output of the turbine times the generator efficiency, gives you the electrical energy output, which is 21.2 into 10 power 6 kilowatt hours, or 21.23 gigawatt hours. It's a lot of electricity. Okay. Now, just to put these numbers into perspective, if you were to sell this electricity at a cost of at the tariff at which Saudi Electric Company charges residential users, 18 halala per kilowatt hour, or 0.18 rial per kilowatt hour, then the revenue that can come from select this electricity at that particular price, selling this quantity of electricity at that particular price, would be about 3.8 million rial. So you're talking about a huge amount of electricity, right? It's absolutely a huge amount. From your calculations in assignment one, for your per capita electrical energy usage, you again can look at how many homes it can power. But yep, that's essentially what we are looking for, right? So if we build a plant like this in Dhahran with 80,000 meters square, it can give you a revenue of 3.8 million real, but it does not come for free, right? So there's also some payback time and other aspects. You have to do a capital investment to build this plant, maintain this plant, and so on and so forth, which you will be exposed to a little bit when you do your project on design of solar PV to meet the energy needs of 1,000 homes. All right, that's it. We will continue in the next class, and we'll discuss about integrating a solar concentrated solar uh, power system with the combined cycle, which is in Dubai and close to Neom, and then we'll do a group activity and conclude this chapter. So that's it for me. Have a nice weekend and see you again.